Okay, today we're going over 11.5 geometric series. So we should know that by now, if we're dealing with a geometric sequence, we know we're multiplying to get to the next term of the sequence. Okay, so for example, if I have the sequence 2, 4, 8, 16, 32, and so on. This is a geometric sequence because to get to the next term, we are multiplying by 2 every time. So that is called our common ratio, R, and R is 2 in this case. Okay, it can be a fraction as well. So for example, if I have 100, and then 50, 25, 12.5, 6.25, and so on, then to get to the next number, you're multiplying by a half. So your common ratio, R, is a half here. So we're dealing with geometric series today, which is going to be based on geometric sequences. Okay, so we're looking at first what a geometric series is. So we need to know the difference between a series and a sequence. So a series is the expression for the sum of the terms of a geometric sequence. A sequence is listing the terms, and a series is the sum of all of those terms. Okay, so if the first thing we're going to look at is the sum of a finite geometric series. So finite meaning that it stops. There's an end to the series. So you're adding up a certain amount of numbers here. So the equation for when we have a finite geometric series is the following. So S sub n is simply standing for the sum of however many terms. N is the number of terms. A sub 1 stands for the first term. Okay. R is standing for the common ratio. And finally, N is the number of terms. So you'd plug it into this formula right here, where S sub n is standing for the sum or the series. And this is going to be specific for a finite geometric series. So we already went over for arithmetic series what the formula is. We went over that in 11.4 yesterday. And today's is going over geometric series. So today's there's going to be two different cases. We're going to have it for when it's a finite series and when it's infinite. So this one is when it's finite, meaning it has an end to it and there's a certain amount of numbers that you're adding up. So let's do an example using the sum of a finite geometric series. So for example, here is what we have to evaluate. We have 3 plus 6 plus 12. If we notice here, all of these terms, to get to the next number, we keep multiplying by 2. So since we keep multiplying by 2, that's telling us that it's a geometric sequence and your common ratio R is 2. Okay, so if we look at our equation for the series of this geometric finite series, we can look at what we have here. We need a sub 1, and we know that a sub 1 stands for the first term. So the first term here is 3. Okay, R is your common ratio, what you're multiplying each one by, 2. N is how many terms you're adding up. So you're adding up 1, 2, 3, 4, 5, 6 different numbers, 6 numbers here, so 6 terms. And then we'll plug everything in. So we're adding it up and we're finding S sub 6. A1 is 3 times 1 minus, we just said that R is 2. I'm going to put that in parentheses so that we know that 2 is going to be to the 6th power, not negative 2. All over 1 minus our R, which is a 2. Okay, so evaluating this here, we can use our calculator. 3 times 1 minus 2 to the 6 is 64. Over 1 minus 2 is a negative 1. I could divide 3 divided by negative 1 is a negative 3 times 1 minus 64 is a negative 63. Multiplying this out, I get a positive 189. So the sum of these 6 numbers here is 189. And you can look to see if it makes sense as well. You know that all of these are positive numbers. So when you add up positive numbers, you're going to get a positive value. They're all whole numbers, which means you should also be getting a whole number. Okay, so make sure that your answer actually makes sense as well. All right, so moving on here. Now we're going to talk about infinite geometric series. So an infinite series means that it keeps going on and on and on forever. So now we're going to determine if it's going to have a sum or not. So there's going to be 2 different cases here. And for both of the cases, you're going to look at the common ratio R. Here's our first case. When the absolute value of R, meaning you take the positive value of R, because absolute value means the distance from 0, and distance is always positive. So when the absolute value of R is less than 1, the series converges, which means it gets closer and closer to the sum S. And we're going to learn how to find what that sum is. Okay, so for example, if I take the numbers, let's say a half, and I add a fourth, and I add an eighth, and I add 1/16, and I'm going to just keep adding more and more numbers. So if we look here, this is a type of geometric series, infinite geometric series, because it keeps going on and on forever. And the common ratio, R, so to get to the next term here, R, we keep multiplying by a half, right? Half times half is a fourth. A fourth times a half is an eighth, and so on. So if we notice here, this, our common ratio R, is a half, and that is less than 1, so therefore it will converge. And we're going to find out how we find what the sum would be. But if we notice here, if I start adding these numbers up, okay, a half plus a fourth, that's really a half, that's really 2/4 plus a fourth is 3/4. That's 0.75. Okay, I could keep adding there. So 3/4. Let's add another term on, 1/8. So plus 1/8. That's really 2 times. We can multiply the top and bottom by 2 to get a common denominator of 8. So this is really 6/8 plus 1/8 is 7/8. And then we can keep adding on 1/16. We'll get 15/16. So if you notice, if we keep adding these terms here, you should notice that it's going to keep getting closer and closer to the number 1 in this specific case. So we're going to learn how we find out what that sum is that it's getting closer and closer to. The other case is when the absolute value of R, your common ratio, and the absolute value of your common ratio is greater than or equal to 1, then the series diverges, which means it approaches no limit, or there is no sum. For example, if I have 2, 4, 8, 16, 32, and I keep adding on numbers, if I start adding these up, 2 plus 4, that will give me 6, plus an 8, that will give me 14. If I add 16, that will give me 30. Add 32, 62. So these numbers just keep getting bigger and bigger and bigger. The more I add on, they keep getting bigger and bigger. And our common ratio here, we keep multiplying by 2. So my common ratio r here is a 2. That's an r. Kind of looks like a square root, sorry. R is equal to 2 here. So if your common ratio is greater than or equal to 1, it's diverging. So this series right here diverges, and therefore it has no sum. There's no sum to find. Okay, so moving on, let's first take a look at whether the series is going to diverge or converge. So what you need to find is r. You need to find r, because then we know from those two cases what r is going to tell you. Okay? And we can keep in mind, if the absolute value of r is less than 1, it converges. And it will be approaching a number, a sum. If the absolute value of r is greater than or equal to 1, it diverges. And therefore it has no sum or no limit. So for this first one here, I want to look to see, what do I keep multiplying by to get to the next term? So if we can't see it right away, I can take my second term, negative 1/3, divided by my first term, 1, and that will give me a negative 1/3. So I want to see which one of these does my r, negative 1/3, satisfy. So since the absolute value of r is less than 1, and that's because negative 1/3, the absolute value of that is 1/3, and that is less than 1. So therefore, this series is going to converge. This converges, and in our next slide, we're going to learn how do we find what it's converging to. This one here, we can notice that it's in summation notation, and it's going from their first term to infinity. It keeps going on forever. So this right here is actually in the form of your geometric explicit formula, which is a sub 1 times r to the n minus 1. So if you saw that right away, you should be able to tell me that your first term, a sub 1, is 5, and your common ratio r is 2. But if you can't find that, then you have to go in and actually find the first few terms to find the common ratio r. So a sub 1, I'm going to plug in 1 for n, 2, 1 minus 1. Okay, so I'm going to evaluate that. So this is 2 to the 0, because 1 minus 1 is 0. Anything to the 0 is a 1. And 5 times 1 is 5. So my first term is a 5. My second term here, I'm going to plug in 2 for n. 5 times 2 to the 2 minus 1. And make sure you use order of operations here. So 2 minus 1 is a 1. 5 times 2 is 10. Okay, moving on here, I'll find a sub 3, my third term. I'm going to plug in 3 for n now. 5 times 2 to the 3 minus 1 here. I have 5 times 2 squared. 5 times 4 is 20. So now I actually have enough numbers to see that my common ratio r is 2. And since r is equal to 2 here, when the absolute value of r is greater than or equal to 1, where in this case the absolute value of 2 is 2, and that is greater than or equal to 1, that means that this diverges. So this has no limit. So this one here diverges, as opposed to the first one, converges. All right, so moving on here, now we're going to find the equation for when it does converge. So this is a sum of an infinite, meaning it keeps going on and on forever, geometric, meaning that you're multiplying by the same number to get to the next term, series, meaning you're adding all of the terms in the geometric sequence. So we can only use this when, this should be an absolute value here, when the absolute value of r is less than 1. So that meant that it converges, right? We just went over that. So if the absolute value of r is less than 1, it converges, and here's how you find the sum. the s, notice that there's no n here. There's no n here because we're just finding the sum that it's approaching. And it's infinite, so we're not adding up a specific number of terms. It keeps going on and on forever. So that means you're going to take the first term, a sub 1, and divide it by 1 minus r. And that's our equation for an infinite geometric series. So let's try some here. So we want to determine whether each series has a sum. So we'll determine that by finding the value of r, or the common ratio. So if the series converges, evaluate the series. Okay, so for this first one here, r, we should be able to see is 2, but if we can't see that right away, we'll take the second term, divide it by the first term, and get a 2. So r is equal to 2, and we know that when the absolute value of r is greater than or equal to 1, that means it diverges, and therefore it has no sum or no limit. Okay? So this one has no sum. Diverges, r is 2. Next one, if we notice here, to get to the next term, if we can't find it right away, then I'll just take the second term, 1/5, divided by my first term. And it's actually really nice when your first term is a 1, because 1/5 divided by 1 is just 1/5. This is not changing yet. Divided by 1 is not changing it. And we know that when I have the absolute value of r less than 1, it converges. So 1/5, the absolute value of 1/5 is 1/5, which is less than 1. So it converges. This is a 5 down here. The denominator, 1/5. Okay, so now since it converges, meaning it's going to get closer and closer to a sum, in order to find that sum, I'm going to use this equation right here. So the sum, s, is equal to a1 over 1 minus r. So plugging that in here, a1, my first term, is 1. I just found my common ratio r. So 1 minus my common ratio r is 1/5. 1/5. And that is a 5, not an s. Okay, evaluating some more. 1 over, I can change this to 5 over 5, so I have a common denominator, minus 1/5. 5 minus 1 is a 4. So 1 over, this is a 4/5. And I know that when I'm dividing by a fraction, I'm going to multiply by the reciprocal and therefore get my sum to be 5 over 4, which is the same as writing 4 goes into 5 one time with 1 left over, 1 1/4. So this is what the sum is actually approaching, 1 1/4. If you keep adding more terms of this infinite series, infinite geometric series, it's going to keep getting closer and closer and closer to 1 1/4 or 1.25. And that's how you do geometric series. Thanks for listening.